Okay, so optimization. Optimization is basically the application of our first derivative test. Okay, so when we optimize something, we're trying to find its maximum value or its minimum value if they occur. Okay, so today's optimization problem is basically now using geometric figures or have something inscribed inside of another figure. So in this case, we have a rectangle. It's bounded by the axis and the semicircle. What length and width should the rectangle have so the area is a maximum? So the issue is that there could be numerous different rectangles that we could draw that fit this description. Like it could look like that, or it could look like this right here, or it could look like that right there. So there's many different rectangles we could draw. We want to know which one maximizes the area but still is basically enclosed inside this semicircle. Okay? So now it doesn't matter which triangle or which rectangle that I draw. Okay? Basically, this coordinate right here, the coordinate xy, should be on this semicircle. Okay? So these top vertices will always be here on this semicircle. This coordinate will always be xy. Now that's really, really important. So just like always, whenever we find optimization problems, we need our primary. Our primary is what we are optimizing. What is it that we're trying to find the maximum or the minimum of? Well, in this case, it's area of a rectangle. So the area is length times width. Okay? Now, the second thing, okay, is we find our secondary equation. Our secondary equation is our limiting factor or our constraint. What is keeping my area from being bigger than it is, that it can be? Okay? And in this case, it's the semicircle. Now, the semicircle, this is part of it, which comes from the circle equation x squared plus y squared equals 25. That's where that equation came from. X squared plus y squared equals 25 gives me the whole circle. Y equals the square root of 25 minus x squared is just the top half of that semicircle. Okay? Which means some of our work is already done for us. Because what's actually constraining my equation is this equation. This is my constraint, or my secondary equation. That is what my limiting factor is. Okay? Now, I still got to get my primary equation in terms of one variable. So, let's say that this is my length and this is my width. Okay? So, you can see right here, this width, this is my width, right? From here to here. This dimension right here, this is the vertical distance, y. Because this coordinate right here, you start here, you go this direction, x, and then you go this direction, y. Which means my length, this part of my length is x. Also, this part of my length is also x, which means my total length is actually 2x. So we go back over here and we look at my area equation. That means my area is now 2x times y. But again, needs to be into one variable, and that's where our secondary equation comes in. Because our secondary equation is already y equals, so we just plug that in. So that means my area is 2x square root of 25 minus x squared. Now that my area is all in terms of one variable, I'm good to go to do my optimization. And again, optimization is basically our first derivative test application. So to find my maximums of this equation, I take the derivative, set it equal to 0, and solve for x. And that will give me my maximums and minimums. So I gotta take the derivative. A prime, the derivative of area. Number one mistake my kids are gonna make is not doing product rule here. So since we have 2x times the square root, we have to do product rule. So the derivative of 2x is 2 square root of 25 minus x squared plus 2x times the derivative of the square root of 25 minus x squared. And I'm going to use this equation, the derivative of the square root of u equals du over 2 square root of u. That is the chain rule variant for the square root function. Okay, so here I go. So the derivative of u is negative 2x over 2 times the square root of 25 minus x squared. So that's the derivative of that part. Now let's do some simplifying. This 2 and that 2 divides out. So I'm left with 2 square root of 25 minus x squared. And this is going to be minus, because this minus here. And then 2x times x is 2x squared over the square root of 25 minus x squared. So this is my derivative. Well, I gotta set this equal to 0. So here we go. Set equal to 0. So what I'm going to do, which is normally most teachers would actually get common denominators with those two. I find it's easier, since I have two terms I'm setting equal to 0, is I move the negative 1 to the other side. 2x squared over the square root of 25 minus x squared, like that. Then cross multiply. So this times that, and that times that. So I get 2x squared equals 2 times 25 minus x squared. Because the square root of 25 minus x squared times this, that's squaring it, right? So I'll get rid of my radical. Now, if you had gotten common denominators, you would have gotten that, basically what we found on top. So now, set it back equal to 0 by moving this 2x squared over. So I have 2, well, let's actually multiply the 2 and 2, so it helps us out. That'll give us 50 minus 2x squared minus 2x squared equals 0. So that means we're going to get 50 minus 4x squared equals 0. 50 equals 4x squared. So that means 50 over 4 equals x squared. So the square root of 50 over 4 equals x. So that's our x value. All right, so now that we have x, we need to find y. Well, we have that nice simple equation right here to find our y value. So y equals 25 minus the square root of 50 over 4 squared. So y equals 25 minus 50 over 4. which ends up being the square root of 50 over 4. Because 25 times 4 to get common denominators is 100 over 4. 100 minus 50 is 50. So same thing. So that's the length. Oh, sorry. That's just what y is. So my width is the square root of 50 over 4, and the length, which is twice the width, or 2x, which is 2 square root of 50 over 4. And that is my answers. There you go. Optimization.